Hello, this is Jack Jackson. Today we're going to be looking at continuous distributions, and we're going to compare and contrast those with discrete probability distributions. We'll be looking at both the probability density function, the PDF, and also the cumulative density function, the CDF. And we're going to see how these things, how they compare and contrast between continuous and discrete distributions. So before we do this, let's just kind of do a real quick review. In the first playlist on the YouTube videos, you will see videos about descriptive statistics. And remember, descriptive statistics, we're talking about where we have a data set from either a population or a sample, and we sort of have information overload, and we want to describe that. And we can describe a lot of things about a distribution of data from a sample or a population. Then our second video set, or second playlist in this YouTube channel on statistics, was talking about discrete probability. So we introduced the idea of probability in a discrete case. Most of the time we were dealing with a finite number of possibilities for the sample size, sample space, and then we did a probability. And basically in probability, again, we know something about the population in general. We know some sort of theoretical setup for the population, and we're trying to describe what would happen with a sample, okay, an experiment, and we assign to that a probability. Now, in the previous playlist, okay, our second unit, we were dealing with discrete cases where there was a finite number, or in the case of a few cases like the geometric distribution, there was it was a countably infinite number. So even though it went on forever, it was still, probability came in discrete chunks. Maybe the x values could be 1, 2, 3, 4, 5, and they go on forever. Or they're just a finite number. Now in this case, this unit, we're going to be dealing mainly with continuous distributions, and we're going to see what happens when we extend this idea to continuous distributions. So let's start by talking about the probability density function, the PDF. Now let's just recall what we had in the discrete case, and we'll see what we can leave the same and what we have to modify slightly for the continuous case. In the discrete case, the y values were the output of the probability density function. They're discrete, non-negative values. In the continuous case, the y values will again still be the outputs of the probability density function. Again, they will be non-negative values, but this time they're usually defined over an entire interval of values consisting of infinitely many values, uncountably infinitely many values. Now, the discrete case, the probability density function, basically we should just get discrete dots, basically, but instead of representing them as dots, we typically represent those as vertical bars. And so we get a series of vertical bars. So the PDF of x is the output of that is the height of the bar on the graph at any given x value. Okay, so it's a vertical bar graph. The graph of a continuous PDF is some kind of a curve. It's usually at least piecewise continuous and smooth. It may have breaks in it, but basically it's pretty much, at least on the pieces, some kind of continuous curve. And the y values on that curve are, of course, the y values of the PDF. Now, how does this relate to probability? Well, in the discrete case, the graph of a discrete PDF consists of a series of vertical bars, as I just said, and the height of each bar is the probability of that particular x value occurring. So the area of the bar is proportional to the probability at that particular value. Okay? Now, if the width of the bars is 1, then the area of the bar is numerically equal to the height of the bar, and that is the probability. So in general, we're finding probabilities. We can add up the areas of the bar, but if they all have the same width, which they should, then you can divide by that common width to get the probability. Probability is actually the sum of the heights of the bars But if you remember, the area of a rectangle, of course, is just the width times the height. And of course, if you then to find the height, you take the area divided by the width. So if all the widths are the same, you can factor that out using the distributive property. And of course, if we want to find areas, then we add up all the if we want to find probabilities, we add up all the areas of the bars and divide by the common width. So we see that the area is not quite the same as probability, but it's very close. It's proportional to it. As long as we divide by that common width, we get the probability. Okay, and of course, if the bars have width 1, then it is the probability. Now, in a continuous distribution, the graph consists of a curve, again, usually at least piecewise, continuous, and smooth. And what we have as a probability over here is an area. It actually is the area. The area between the curve and the x-axis from A to B is the probability that the random variable will take on values between A and B. But notice over here on the continuous case, y values are not probabilities. In the discrete case, y values are probabilities and the height of the bar, whereas in the continuous case over here, the y values are the height of the curve, but they are not probabilities. Let's look at a picture. Make a little bit more sense once we see a picture. So probably the most important class of discrete distributions are binomial distributions, which we studied in our previous unit. And the most important distribution, period, continuous or discrete, and certainly the most important continuous distribution, is a normal distribution. This is a standard normal distribution here. It's a bell-shaped curve. So y values here are not probabilities, rather they are the areas of probabilities. So let's look at the binomial distribution over here to the left. If we want to find the probability that x is, say, between 14 and 17 inclusive, we take the bars for 14, 15, 16, and 17, all the bars that exist between 14 and 17 inclusive, find the heights of those bars and add them up. Now, since the bars' widths are 1, it's the same as adding up the area of these bars. Now, if you can imagine this happening where we take more and more and more and more bars and maybe smaller and smaller widths, then these things would start to smooth out a little bit. The top of this curve actually looks a lot like the normal curve. It would kind of smooth out and approach a curve that looks like this. So with that idea in mind, we can use a continuous distribution sometimes to represent the probability of some kind of real-world thing where it's actually, maybe it's actually really a discrete possibility, but we have use a continuous distribution to model that, or maybe there really is a continuous type data, and we'll use a continuous distribution. So here's a standard normal. It has a mean of 0 and standard deviation of 1, and this shaded region right here represents some area, and notice it's the area between the PDF graph and the x-axis, and then from the x value lower to upper. So the x goes from 0 to 2, so we look at the vertical line at x equals 0 and x equals 2, and then the PDF curve are the boundaries on the top, and the y equals 0, the x-axis is the boundary at the bottom. The two x values, those vertical lines, give you the boundaries on the left and right. That creates a region here that we can shade in and compute its area, and that area is the probability that the random variable x will be between 0 and 2. So in both cases, areas are sort of probabilities. In the right case, the areas are probabilities in the continuous graph. On the left, in the discrete case, the areas are at least proportional to the probabilities. So, once again, the output of the PDF function for a discrete distribution is the probability that the random variable equals that input value. It's also the height of the corresponding bar in the graph, and it is the area of the bar divided by its width. So if you want to find the probability that x equals some number a, you just find the PDF of that a. So in the discrete case, remember, PDF of a is the probability that x actually equals that a. But we get a strange phenomenon that happens in the continuous distribution. And this, I know this one takes a little while to get your mind around here, but since probabilities are represented by areas between the PDF and the x-axis, what if we wanted to find the probability of a specific point, like say the probability that x equals 2? Well, you draw a vertical line at x equals 2, and another vertical line at x equals 2 and find the area between that and the PDF and the x-axis. Well, that little thing that you just drew is a line segment. A line segment has no area. There's no width to it. So you have 0 width times whatever height is still 0 and 0 area, and so that makes 0 probability. So the probability that x equals a specific number a equals 0. Kind of strange there, but it actually turns out to be the case, and that's the case for any continuous distribution. For example, the probability that x equals 2 is 0 no matter what the distribution is if it is a continuous distribution. Another way to think of this is, if we want to, in the discrete case, you can think of the probability as taking the probability that x equals a. If it's let's say a finite case, it's basically the size of the event a, and then divide by the total size of the sample space. Well, you can think about it over here in this case, in the continuous distribution, you're dividing by an infinitely big sample space. Essentially dividing by infinity more or less gives you something kind of like 0 there, at least it approaches 0. So that's sort of another way to think of it. But it turns out that either way you think of it, the probability that x equals a specific number is 0. Okay? Now, you say, well, wait a minute, couldn't x be 0? Well, couldn't x be 2, for example? Well, what you typically do in a continuous case is you round off. So you could say, well, what's the probability that x rounds off to 2? Well, that you can do, because that would be the probability that x is between 1.5 and 2.5. In other words, probability that 1.5 is less than or equal to x, which is in turn less than 2.5. That does have a width of 1, and in many cases that does have some probability associated with it, so it's typically not 0. So you can talk about probabilities on some little interval and say, well, all of these are considered 2. Then you can talk about that probability, but the probability that x equals 2 exactly, that's 0. Kind of strange, but there it is. Now, the next thing we can talk about, the probability density curve. This is the CDF. This is mislabeled here. This should say CDF. So, well, actually, this is still, I'm sorry, we're still thinking about the PDF. If you're finding probabilities between two numbers, A and B, for the probability density function, this is the PDF, then you're going to add up the values of the PDF, all the ones that are in that interval. So if you take all the x's that are between A and B inclusive, you find their PDF values and add them up. Then that gives you the probability. So notice that the Greek sigma is a capital Greek letter sigma, and it's sort of a Greek version of our Roman letter S, standing for sum. So in this formula above, this sigma means add them up. Okay? It means sum up or add up the discrete probabilities for each individual one. Now, how does that translate over here to the PDF of the continuous case? If we want to find the probability that x is between some value a and b, we want to sum up the PDF in this case. And the notation we use for that, again, we use an S. Over here we used a Greek S, a sigma, capital sigma. Over here we use a long skinny s. This long skinny s is called an integral sign. And it is a stylized S for sum. And so what we're doing is we're summing up our probability density from A to B. So basically A to B. This dx over here for our purposes is basically notational. It's basically telling us that the x is a variable, and so the dx is just identifying what the variable is. But we're summing up our PDF. Okay? So over here in the discrete case, remember that your probability comes in discrete chunks. So every time we add in a new x value, either we're not adding any probability, or we're adding in, if the probability is 0, or we're adding in a whole bar at a time. So your probability comes in chunks, a whole bar at a time. Over here in the continuous distribution, the probability density is kind of spread out more smoothly, and you're adding it up in more of a flow, a continuous flow. So if we look back at our picture here, if we're going along and we're adding up this probability between here and here, we're adding up the probabilities. This probability density you might think is coming in these bars, and so when you go across and you add them, either you add a whole bar or you don't add anything. So we're adding a whole bar each time we go across, so this probability jumps up in chunks. Whereas over here we're adding, it's more smooth. Think of this as like adding one peanut at a time, and this is more like adding peanut butter that's spread out, so that we're adding it up in sort of a continuous flow, whereas over here we either get a whole peanut or not, a whole bar actually of probability density, as opposed to some smooth amount over here. Now, if you've had some calculus before, you may recognize this integral sign as a very important thing in calculus. Now, in these videos that I'm going on, I do not assume that you have ever had any calculus, and we do not need to know all the details from calculus about this integral here. What we need to know is this is just a notation for summing up probability in the continuous case, and this is, or if you think of it in terms of the PDF, we can think of this as an area calculator. It's the area between the PDF curve and the x-axis from A to B. So think of this as this is our area calculator. This is our sum. This actually could also be summing up the areas here and then dividing by the width. Now we also have some formulas for finding certain parameters. The most important two probably are the mean and the variance. Of course, variance, we can get the square root of the variance is the standard deviation. So remember that the mean is the expected value of x. So in the discrete case, what did we do? We took the x value times the probability of that x value, which is just the PDF of x, and we summed that up over all possible x's. Every x that was actually possible, we summed that up, and that sum then becomes the mean, which we represent by the Greek letter mu. Remember, when we're doing a distribution like this, it's essentially a population, so we use the Greek letters mu for mean and sigma for standard deviation of a population, not x bar and s, which would be for a sample. Now, how does that turn into a formula for continuous distribution? Well, to find the mean, we still use the letter mu, we still call it the expected value of x, and we're still summing up x's times probabilities. So what do? We sum up x times the probability of that x, the PDF of x, with respect to x, dx, and we sum that up from forever left to forever right, from negative infinity to positive infinity, which will cover all possible x's. Now, in some cases, if the PDF is 0, then at certain x's, then that doesn't add anything to this sum, so we can ignore those. So, for example, if the PDF was 0 for negative x's, we could just start this sum at 0 to infinity, because the part from negative infinity to 0 is just adding 0 to the sum. There's no area over there to calculate. Okay? And this would be an area not under the PDF graph, but under the graph x times PDF of x, if you wanted to think of it as an area. But we'll probably just think of it as this formula right here. Okay? Now, what is the variance? The variance is the square of the standard deviation. It's sigma square, and it's defined to be the expected value of x minus mu square. If you remember when we computed this, we took x minus the mean for every point we took every x sub k, we subtracted the mean. Of course, first we had to compute the mean. Then we do x sub k minus the mean, then we squared all those. Then we took each of those squares and multiplied them by their probabilities, which is the PDF of that x sub k. And then we sum up all those products for all x sub k, and that gave us the variance. Of course, just take the square root of that, and you get the standard deviation. That's what we did back in the discrete case. How do we extend that to the variance in the continuous case? Well, again, it's still called sigma square. It's still called the expected value of x minus mu square. And we're still taking x minus mu square, multiplying by the probability, the PDF, but then we're summing it up. The summing it up in the discrete, the continuous case was this integral from minus infinity to infinity. The dx just tells us x is our variable, and then this tells us we're doing all possible x's here. We'll come back to working with this in later videos. Okay, now how about the cumulative density function, the CDF? So we've been talking about the PDF, the probability density function. What about the CDF? Well, the CDF of A is the probability that x is less than or equal to A. So probability x less than or equal to A is the CDF of A in the discrete case. Guess what? Continuous case? Exactly the same thing. The probability that x is less than or equal to A is the CDF of A. So both of these are the same in that respect. What is it? What is CDF of A? How does that connect to the PDF? Well, the CDF of A is the sum over all x's less than or equal to A of the PDF. So you take the PDF and evaluate it at all x values that are less than or equal to A, find all those outputs, which are probabilities of those individual x's, and add them all up. Well, what do you do over here? Well, not too surprising. You want to calculate this sum, but all the x's up to A. So you go from negative infinity to A on our sum, and then we sum up our probabilities, PDF of x, dx. Okay? So the graph of a discrete CDF is a step function starting with a horizontal ray pointing to the left at a height of 0 on the x-axis, and ends with a horizontal ray pointing to the right at a height of 1. Between this graph is a sequence of horizontal line segments open on the right and closed on the left, stepping up at each x value that has a non-zero probability. We'll look at the graph of that in a minute. In the continuous case, this is where the word continuous really applies. It sometimes applies to the PDF, but not always. But it definitely always applies to the CDF. The graph of a continuous of the CDF of a continuous probability distribution is a continuous curve, meaning it basically that you can draw it without picking your pencil up. So there's no breaks in it at all. Okay? It's also non-decreasing. The graph here on the discrete is also non-decreasing. It starts at 0 and always steps. It's level for a while and then makes step, level, step, level, step, level, and it ends at 1. The graph of this one here, it could be level at places, but it never goes down. So neither one of these graphs of the discrete or the continuous CDF, they never come back down. Once they get to a certain y value, they only go up. And they start at 0 and end at 1. Now, in the case of a continuous CDF, it may not actually be 0 on the left. It may actually be 0 on the left, but it may also have an asymptote of 0 on the left. And again, we have two options. It could either be 1 on the right, or it could have an asymptote of y equals 1, approaching that. Okay, now, if you've had calculus before, I'm going to make a statement that may help you understand this. If you've not had calculus before, completely ignore this statement. Makes no difference. The CDF is actually an antiderivative of the PDF, a specific one. Okay, this is an antiderivative. And the PDF is the derivative of the CDF. So if you know what those words mean, that you can make sense of that. If you don't know what that means, totally irrelevant. We can go along with what we've got here. So let's take a look at what the graphs look like. So on the left you see a cumulative density function, a CDF for a discrete case. Notice the characteristics. It's the kind of graph we call a step function. Now I'm defining this for all real numbers, not just the places where the probability actually changes. Not the x's, just at the x's where it has probability changes, not just those, but all of them. So if you look at that, the first place we actually have some probability here is, it looks like 2 right here, this first step, first break in the graph. To the left of that, the probability that x is less than 2 is 0. So you get this horizontal ray going out forever to the left on the x-axis at 0 probability. Now when it actually gets to 2, there's an open dot there, and it steps up here and has a closed dot because at 2 there is some probability. Now there's nothing between 2 and 4, so it stays, the cumulative probability stays the same. So the probability that x is less than 3 is the same as less than or equal to 3 is the same as the probability that x is less than or equal to 2. It stays the same because the only thing below that that actually has a probability is x equals 2. Then when it gets up to the next place where we have some probability that actually happens, it steps up again, and then it steps up again and again. And when it makes the final step, it's always at y equals 1. This horizontal line at the top is y equals 1, and we're always at a ray there. So your cumulative density function always looks basically like this for any discrete case. You always have a ray to the left, you always have at 0, you always have a ray to the right at 1 where it ends, so it starts at 0, ends at 1. Now the number of steps and how big these steps are is going to depend on what kind of distribution you're looking at, but they all basically look like this. They're a bunch of stair steps. Okay? Now on the continuous distribution, you actually have a continuous function. This discrete case, you definitely don't have a continuous function. You have a break. You can't draw this without lifting your pencil because you have breaks here, discontinuities. Okay? Over here we have it's continuous. Now this particular one actually is 0 over here to the left up until a certain point in here, somewhere in here, in which case it starts to increase. And at some point, right about here, it actually hits 1 and stays 1 from there on out. But you can also get a graph that looks very similar to this, where this on the left might actually not be equal to 0, but actually is an asymptote of 0 as you go out to the left. And as you go out to the right, this may not actually be 1. In some cases, it may actually have an asymptote of 1. But otherwise, they all basically look the same. They start down here at 0. Somehow, in some connected way, they come up and level out or just become level at 1. So they start at 0, go to 1, basically increase the whole way, or it could have sections where it's horizontal, but it never comes back down. And again, once you make a step up here, it may stay there for a little bit, but once you make a step up, you never step down as you go left to right. In the discrete case and in the continuous case, it always goes up left to right. So that's what they look like there. Okay, let's examine the CDF and PDF connection for a discrete case first, and then we'll do the same thing for the continuous case. Now remember that the CDF is the probability that x is less than or equal to a. It's a left probability, a cumulative probability, probability to the left. So the y value on the CDF graph is the same as the sum of the heights of the bars on the PDF graph. So here we have a graph of a probability density function, and I have both the PDF and the CDF graphed. So here I have the x values, 2, 4, 7, 9, and 11 that actually have non-zero probability. Here are their probabilities. This is actually in a dynamic sketch so that I can change these numbers, but notice I can't change this one because what do you know about these probabilities? Well, they have to add up to 1, of course, and once I set the first 4, the last one, I don't have a choice. And the CDF then, 0.2 is this 0.2 here, same as that. CDF for this one is going to be these first two added together, 0.2 and 0.1, which is 0.3. Then add these 3 together, you'll get this one here. And add these 4, you'll get this one. Of course, the last one you get that actually has some probability, if you got these organized left to right on the graph, the last CDF will be 1. And if you do a CDF of anything less than the first one, it would be 0. So it essentially starts at 0 and goes up to 1. So the red graph is the CDF graph, and the blue graph is the PDF graph for this particular one. Now let's look at this a little bit more. So once again, to see the connection here, so the CDF graph starts at 0 where we have no bars. When we get up to a bar, we put an open dot there, and we go up by the same amount of the height of that bar. And then we stay there until we get to the next bar. And then we go up by the height of that bar here. So this little blue bar right here at 4 and the little purple bar are the same size. And you notice that the amount of the step is the same as the height of the bar. And we stay there till we get to another place where we actually have some probability. In this case, it's at 7. And the probability at 7 is 0.05. So the height of this bar is 0.05. This little purple height, which is just move this bar up, that's our difference between our steps. That's the size of the step. Okay? And that's, again, 0.05. We made up to that step. We go over here, the height of the blue bar from here to here is the same as the purple bar from here to here. And finally, the last one is the same as that one. So hopefully with that you can see the connection between those two graphs. Notice once again, once we get at 4, since the cumulative probability does include the point at 4, we have the closed dot at the higher level here, because we've actually, the y value in the CDF is the probability that x is less than or equal to the x value. So say the probability, the CDF of 4 is the probability that x is less than or equal to 4, so it's going to include both of the heights of these two bars essentially stacked on each other, or a vertical change of this height plus this height more. Okay, so once again, let's look at 3 different types of probabilities. A left probability, a right probability, and a in-between probability, middle probability. So first of all, let's do a left probability. The CDF of A gives you the left probability. In other words, the probability that x is less than or equal to A. Okay? It's the sum total of all probability density to the left of the input value. It's the total probability to the left. Okay? So in this example, for example, we have below the CDF of 9. So you find 9 on the graph here. And the CDF of 9 is this red, it is this y value right here, which you can see is 0.75. Okay, and how can we see it? Well, we can see it as this orange length. So a vertical length from 0 up to the y value, which is the same as the y value, is how we see the probability on the CDF. How do we see the same probability on the PDF? Well, the PDF, we see it as the areas of these bars, actually the heights of the bars added together. So it's the height of each of these 4 green bars, which are 0.2, 0.1, 0.05, and 0.4, and those add up to 0.75. Okay? Or add the areas of those 4 bars and then just divide by the common width. In this case, the width is 1, so when you add up the areas, you get the probability as well. But on the CDF, we see it as an orange length here from 0 up to the y value, or we see it as an actual y value. Again, CDF is the probability to the left. So notice all the green bars are at or to the left of the x value that we're talking about. CDF of A is the probability that x is less than or equal to A. Now what if you want to go to the right? What if you want to find the probability that x is greater than A? Well, we can use the complementary probability, right? So the probability that x is greater than A is 1 minus the probability that x is less than or equal to A. Because either x has to be greater than A or less than or equal to A. That's your only 2 possibilities. So those 2 probabilities have to add up to 1. So this probability, the probability that x is less than or equal to A, that is just CDF of A. So if you want to find the probability that x is greater than A, you can do 1 minus the CDF of A. So, for example, below, if we want to find the probability that x is greater than 9, we can say that's 1 minus the probability that x is less than or equal to 9, which is 1 minus CDF of 9, which is 1 minus 0.75, which is 0.25. Now, how can we see that visually? Okay? So, we see that as this brown length. We take this y value on the CDF, and we find the length, the distance from that up to 1. So remember, this orange length is the probability to the left, and with the difference of that from 1 is this brown length from here up to here. And that brown length is the 1 minus the CDF, so that's the probability to the right. What does that correspond to on the PDF? It's the sum of the heights of the bars to the right of this. Since I said strictly greater than, we don't count the one here at 9. We want to eliminate it. We want to count strictly greater than that, to the right of that, which in this case is only the one bar, which has height 0.25. If there were more bars to the right, we would add up the heights of all of them. Or alternatively, same thing, add up the areas of those bars and divide by the common width. Since the common width is 1, this area of this bar is the same as the height, which is 0.25, which is the probability we're looking for. Now what about a probability in the middle? Not to the left, not to the right, but between two numbers. So say between two numbers A and B. So if we say A is less than X, which is less than or equal to B, specifically that kind, then we're finding the probability that X is less than or equal to B, which would give you everything to the left of B, but then we've counted this to the left of A, which we didn't mean to. And so we want to have to subtract off the probability that X is less than or equal to A. Well, this probability that X is less than or equal to B is CDF of B. Probability that X is less than or equal to A is CDF of A. So we're doing the difference in those two CDFs. So look at the graph again below, same distribution we were looking at. What if we want to find the probability that 3 is less than X, which is less than or equal to 9? So the probability that X is between 3 and 9, not counting the 3, but do count the 9. So we want to count all bars that are bigger than, the X's are bigger than 3, less than, but also less than 9 or equal to 9. And if you look, that's these 3 green bars. So on this PDF graph, we're adding up the heights of these 3 green bars, which are these output values, adding up the Y values, 0.1, 0.05, 0.4, which is 0.55. Okay? And we can see it as these the heights of those 3 bars, or we can also see it as the areas if we divide by the common width. Again, the width's 1 here, so if we just add up the areas of those 3 bars, we get the probability, divide by the common width of 1, doesn't change the number in this case. But if the widths weren't 1, we would have to adjust by that factor. Now, how do we see that on the CDF graph? Well, remember this orange length from here, from 0 up to the Y value in the CDF graph, was the cumulative probability up to that point. That would be the total area to the left of that point. But we've counted this part here to the left of 4, and so we can take a point here in between, say at 3. Here's 3. Probability that we're less than 3, there's nothing at 3, so that it's just this probability over here. So we can find that, okay, which is 0.2, and the probability to the left of 9 was 0.75. If we subtract those two things, we get the probability between, which is represented by the 3 green bars in the PDF. On the CDF, it's represented by, look at these 2 Y values here, the Y value at your endpoint here, and your Y value here, and the difference in those two is given by this green vertical length. So that green vertical length is the probability between the two. But again, you can find it by just doing the difference in the two CDFs. Alright, now how does this translate over to a continuous distribution? Okay, let's again do the 3 cases, probability to the left, the right, and the middle. So the probability to the left, okay, now this time, remember the probability that X equals A is 0. So it really doesn't matter whether we're talking about the probability of X is less than A or the probability of X less than or equal to A, they're the same thing. The probability that X equals A is the only difference, but that's 0, so that means there is no difference. And that is the cumulative probability to the left of A, and that is the Y value on the CDF graph. So CDF of A, remember, equals the probability that X is less than or equal to A. So here we have in blue a PDF, and in red, they're both identical right here. They're both 0 here until we get to this point A, which is 3. and then this one goes up here and ends up here. So the CDF is the one that's going to start at 0 and go up to 1. The PDF is down here. So the CDF starts at 0, goes up to 1. The PDF is the blue one. CDF is the red one. So the PDF is down here, and it's going to make some area. And what's this total area of this basic triangle shape? Not the shaded part, but the total area. Well, there's 0 area out here to the left of A. There's 0 area out here to the right of B. But in between, we've got a triangle region, and that represents the total probability. Well, you add up all the probability, and you get 1, 100%. Right? And so this total area is 1. Now, if we want to take a particular x value, like this x value right here, this x value here, on the PDF graph, if we want to find the probability that x is less than or equal to a, or x less than a, same thing, it's the probability to the left of this thing. Remember, on the PDF graph, probabilities are areas. So here we have an area to the left, below the PDF graph. So the blue graph is the upper boundary. The lower boundary is the x-axis. The right boundary is my x value, vertical line there. And there is no left boundary. It goes forever left. Now in practice here, since there's nothing left of A, it's really the same as the probability of just A up to this x value, which I think is 11 here. Yeah, it's 11. And then we can go up. So that area is the probability. It turns out to be 0.87 or 87%. Now, if you go up here and find the y value on the CDF curve, that y value will be the probability. So that ordered pair of that point x is 11, 8.7. So actually the x value of the random variable is 11. The probability of that x value, not of that x value, but less than or equal to that x value, is the 0.87. So the probability that x is less than or equal to 11 is 0.87. The probability that x is strictly less than 11 is also 0.87. How do we see that? Well, we see that as a y value here, right here, which we can also see as a vertical distance. It's a distance from the axis up to that point. So that orange distance, that vertical distance, on the CDF graph is a cumulative probability. The shaded area under the PDF graph is the same probability. Once again, PDF, areas are probabilities. CDF, y values, or vertical distances, are probabilities. Well, what if we want to do a probability to the right? Okay, so now we're talking about the probability that x is greater than or equal to a, or in other words, the probability that x is greater than a, because, again, probability that x equals a is 0. That turned out to be the same as 1 minus the probability that x is less than or equal to a. Well, the probability that x is less than or equal to a left probability, is a CDF. So what we have here is 1 minus the CDF of a. And that will give us the probability to the right of a. Now, how do we see that visually? On the PDF graph down here in blue, it's the area to the right of the orange line. So it's this unshaded triangle area right here under the blue curve, this part right in here. So that area right there, which turns out to be, I guess, about 0.13, 13%, that's the probability. We can see it as an area under the PDF graph. For the CDF graph, we see it as a vertical distance. Not exactly a y value, but a vertical distance. So the y value here of x is 0.87. That's the probability to the left, the same as the shaded region on the PDF. Well, if that's the probability is represented by this orange length from here to here, remember this horizontal line right here is at y equals 1. So the length from 0 up to 1 is the total probability of 100%. Well, we've already gone over 80. We've gone up to 87% to the left. So what does that leave to the right? The difference, which is given by this brown line segment here, which is 13%, 0.13. And so we see that the vertical distance, again, a vertical distance is the probability we're looking for. In this case, since we're going to the right, it's the probability, it's the vertical distance from that x value, from that point on the graph up to y equals 1. Whereas if we're just doing the CDF, just straight out CDF of x, that's the probability to the left, which is the vertical distance from the x-axis up to the point. Okay, one more example with these. What about a continuous distribution and we're trying to find the probability in the middle? Okay, so what's the probability that A is less than X is less than B? And again, whether or not we include the two endpoints is irrelevant. So say that's the same as the probability of A less than or equal to X, which is less than or equal to B. So you can think of it as an open interval or a closed interval, or you can do half open, half closed. Probability of A less than or equal to X is less than or B, or the probability of A less than X, which is in turn less than or equal to B. Doesn't matter. So what is that? What do you get from that? Well, it's the same as the probability of X less than or equal to B minus the probability of X less than or equal to A. Well, if you think about this one here, probability of X less than or equal to B, that gives you the probability from B forever left. But that counts too much. We want to subtract off the probability that X is less than or equal to A, and what's left is the probability that's between the two. Well, now each one of these things, since it's a left probability, that's just a CDF. Okay? So CDF of B minus CDF of A is the probability to the right of A and left of B. Okay, I should say between A and B. I need to correct that slide. On the CDF graph, how can we see this and how can we see it on a PDF graph? Let's start with the PDF graph. So here we have some A and B. Looks like I've got 10.5 to 11.5 for our A and B. So what's the probability that X is between 10.5 and 11.5? That's where we draw these two vertical lines. And those two vertical lines give us boundaries. The top of the curve of the PDF curve gives us, this blue curve gives us an upper boundary, and of course the x-axis is our lower boundary. That gives us this green region. The area of that green region is the probability. So once again, on PDFs, areas are probabilities. So the area between x equals A and x equals B and the PDF graph and the x-axis, that green area is that probability. It turns out to be about 0.1317 here. Okay. Now, how can we see that on the CDF graph? Well, remember this purple length from here, from the x-axis up to this point, is the cumulative probability up to well, whatever that x is, b 11.5. So that's the probability that x is less than or equal to 11.5. Well, what about the green distance from the x-axis up to this point here? That's the CDF of 10.5, and that's the probability that we have less than that. So how would that correspond to areas down here on the PDF? So these are just y values on the CDF. So this y value at the right on the CDF is the probability less than that x value, less than 11.5, which would be this green area and this other area here, everything to the left. But if we subtract off this unshaded area right in here, which is from 10.5 down, what will remain is the green area. Well, what does that do in terms of the y values? When you subtract this y value minus that y value, you find the vertical distance between them, which is that green line segment. So once again, we can see the green. We can see a green line segment here. That line segment, that vertical line segment, the length of it is a probability. So on the CDF, we see a vertical length as a probability, and on the PDF, we see an area as a probability. So in general, in a discrete probability distribution, the PDF, the probability density function, probabilities are sums of y values. That is, the sums of heights of bars on the PDF graph. Or we could think of it in areas as the sum of the areas of the bars as long as we divide by the common width on the PDF graph. The cumulative density function, left probabilities, probabilities to the left, less than probabilities, less than or equal to probabilities, are actually the y values. And we can see them as vertical distances on the CDF graph. On the continuous case, the CDF basically works the same way. Cumulative or left probabilities, less than or equal to probabilities, are y values, and they are vertical distances on the graph. So that's the same in both cases. However, up here, the PDF graph, it's the area between the PDF graph and the x-axis is the same. This is the area that is the probability. In a way, those are the same too if you're careful with it. The continuous case, areas are probabilities under the PDF graph, and if you do the areas of the bars over here, you just got to remember to divide by the common width in the discrete case, and you've got a probability as well. So, if you remember, we looked at several different kinds of probability density functions in the discrete case, and some that we studied are discrete uniform, where all the bars were the same height. And then we studied just some finite ones, just sort of sporadically or randomly given by a table, where we actually just listed out all the values, kind of like the one that I was using for an example in this video. And then we looked at some standard kinds of situations, geometric, binomial, hypergeometric, negative binomial, and Poisson. And we have videos in our discrete distribution case over each one of those. Now, some continuous distributions that we might look at are uniform distributions, or the continuous uniform distributions, triangular distributions, exponential, normal, T, F, chi-squared, and beta distributions. Okay, I will probably in this video not talk too much about beta distributions, but normal, T, F, and chi-square are very important for statistics, especially the normal one. And exponentials use some. Uniform and triangular are not quite as important, even though there may be some real-world examples that follow one or the other of these. But these are mainly used to help us work through this if we have the PDF given, because these have very simple shapes. Uniform is just a horizontal line segment, or piecewise horizontal, basically, piecewise constant function. And so we basically end up with areas of rectangles when we start trying to find probabilities. Well, rectangles are real easy to find areas of. So we'll start with uniform when we get to start working with PDF functions. Triangular are going to be introduced for basically the same reason. So the example that I used in this video for the continuous distribution was actually a triangular distribution, and you can kind of see why, because there's a little triangular area there that we were looking at. And so why do we study that one? Well, again, it's just something that's easy to actually compute the areas of. And generally speaking, it's very difficult to compute areas unless it's a very nice shape. Rectangles, right triangles are very nice shapes. We'll work some with those first. And then after that, we'll probably use some technology. Luckily, there's a built-in area calculator, a numerical integration technique on your calculator that we'll eventually use. Okay? Now, we need in the next videos to start talking about working with these a little bit more. So first, we're actually going to work with the CDF graphs and try to come up with how we can find probabilities and inverse probabilities from the CDF graph. And we're going to start with that because the CDF graph is actually much easier to use than the PDF graph. And so we're going to use that starting from some examples that are graphed and some formulas where we can get the graphs. And we're going to learn how to find probabilities and inverse probabilities from the CDF graphs first. Then we're going to go to PDF graphs after we have mastered CDFs, and we're going to start with uniform and then triangular distributions where the areas that we have to compute are more easily computed. And then we'll learn some calculator techniques that allow us to expand out to some other distributions. So that's kind of what we have to look forward to in the next couple of videos.